I'm an NLP researcher, joining recently the robotic fields in some applications, and sometime I might be used of terms in robotics, so be nice with me if I fail on some words or sentences. But just to synthesize what is the objective of the Pillar Robots project is to design autonomous robots with the objective that they can handle different situations that they haven't seen before, and therefore we have also a lifelong learning objective issue. And the role of NLP in this project is, this is a particular task within the project. There are other challenges, but the one related to NLP is to assume that we have a goal expressed in natural language. So you might have some, we might have some redundant things with the Cordelia talks, but the objective is to provide some grounding in terms of environment, providing the semantic representation of objects and the scene, and also to generate the sequence of actions in natural language or logical actions in terms of commands for robots. And for doing that, we use large language model, obviously, and just to be sure that everyone is okay with large language model, I will take some time to say what is it, and more particularly what are their interesting abilities and how we can use them for robotics. So here, just the principle of large language models. The objective is to model the probability of a sequence of some things. Something can be the words, the characters, or tokens also. Now we use tokens for a large language model. And you have an example here. So I have the beginning of the sentence. And the objective of the large language model is to provide the probability of different tokens or different words to end this sentence. And for doing that, the backbone architecture is the transformer networks, which is a huge encoder-decoder with different successive feed-forward blocks and also parallel heads. And in transformer, we have something that is quite interesting, which is called self-attentions. In self-attention, the objective is to estimate the contextual representation of tokens according to the different tokens within the sentence. And particularly, this allows we cannot see in the back, but it allows to distinguish when we have the word, for instance, Washington, distinguishing whether we speak about the city of the man, and we call that polysemy of words. Transformer has been used in the beginning in NLP, but we have seen that it provides very effective results in different tasks, and now this is mostly in use in most of the tasks. And the question we can wonder is what we learn from a large language model or language model. Since it predicts the probability of the next token, we can see at the short context point of view, and we assume that it predicts, it captures some grammar, verb conjugation, knowledge and semantics around the words. But when we see in this tree, we started with a quite small transformer, and now we have large transformer with an increasing numbers of parameters. And in the beginning, it was mainly used to capture the semantics and to solve very simple tasks in NLP. And now we have complex tasks that can be handled in NLP, such as reasoning, summary, also numerical reasoning, and also code programming, and so on. And the question is it simply a capture of short context? And in our opinion, and it is also related in some paper, we think that it captures some meta pattern in kind of long text context. For instance, for doing an enumeration, you have the structure of the enumeration and it can capture this. Also, when you provide a document to a transformer, it captures the structure of the document, but also the way to relate a story within this document. Obviously, this concept of meta pattern is quite obscure, and we have to go deeper into the analysis of this concept and to better understand what a transformer capture. But this concept allows to tackle a large variety of tasks. And for instance, also, it is possible because they are what we call emergent abilities of large language models. We have identified, some papers have identified that when you increase the number of parameters, then you can solve in a zero-shot setting new tasks that are very complex. And here, this is an example. So I took a reasoning task in which you have a question and in text and that asks some reasoning in terms of doing some addition, multiplication, and so on, so numerical reasoning. And what is highlighted also in some papers is that you can provide some example of planning or process you have to do to perform this task. So here, this is a question about how many tennis balls do we have now. So it's kind of a tricky mathematical problem we have when we were very young. And in the answer, they provide some example of how we can obtain the final answer. So here, this is by doing an addition between two terms. And then when you provide a new question, the model is able to provide the process to obtain the final task. And we have highlighted that by doing these reasoning steps, so we call this chain of thought reasoning, the relevance of the answer is increased. Compare when you provide it. And what is interesting also is that when you do not provide this process as example, but you just, where is here? When you just provide, when you just ask the question and you provide the beginning of answer, which is let's think step by step. So you don't have the process as example, but you ask the model to think and to decompose the process, the answer has different steps. The model is able to provide these reasoning steps and then to provide the final answer. And that's is also linked to the fact that we call meta patterns. The model has identified what step-by-step means according to the different examples which has been provided to train the model and understand or capture that you need to provide a process to feed the answer. So just a summary, a slide with some interesting properties of large language model. Obviously, you might know the property of prompting, in which you provide explicit instruction to the model, and then it is able to perform the task. The other property is a scaling law. Some analyses have been done analyzing the impact of increasing the number of parameters within the model. And one main conclusion is that when you increase the number of parameters within the model, you need fewer data points and less epochs to train the model to have reasonable effectiveness results. And you obtain similar results as a small language model. So on the left, you have the large language model, and on the right, the smaller one. And you obtain similar results as small model, but with fewer epochs and less data points. And the third properties I would like to mention is the in-context learning property. The objective is to provide different examples within the prompt. So you have here the question, the answer. So here this is a visual task in which you ask to predict the emoticon associated to the image, but you have one question, the associated answer, a question, the associated answer, and so on, until you provide your own question. So here, this is the question and the beginning of the answer, and you expect the language model to predict the associated emoticon. So we call that in-context learning, or also few-shot learning. And if I would like to synthesize how we use and how we train those models, so we use large collection of documents, and for pre-training those models, we use either masking, so we mask one token within the sentence, and we hope that the model predicts this token, or also we can use what we call causal pre-training, in which we provide the beginning of the sentence and we hope that the model predicts the next token in the end of the sentence. So we have kind of pre-trained large language model, and we assume that in this language model we have kind of general knowledge related obviously to the data you provide in the model, but it captures those general knowledge. And at the end, you can fine-tune this model if necessary on your targeted task. But what is interesting, you don't need a lot of data. You need just a small few set of data. And this might be sufficient to fine-tune the model to perform your task. So the question is, what about LLMs for robotics? So I take the same task as Cordelia has described. You have a robot and a scene, which can be in 3D, obviously. And we have a specific goal, and we ask the robot to perform this scene. And the standard pipeline aims at producing logic action or commands that might look like this, and then you can make controller to make the robot evolve within the scene. Where can we use large language model, in my opinion, and maybe this is not the whole possibilities, but the one we have discussed already is to generate the sequence of instructions and decompose a complex goal within subtasks to be performed. And in the end, we have to map natural language with those logic actions. So this is also a challenge when we generate natural language instruction. Oops, sorry. And the second one is to allow the robot to interact with something external, which might be humans. For instance, if there are uncertainty in the task definition, you can ask humans what is the real intent behind the goal, or also interacting with the environment to refine the plan. So some example here, this is a Alfred dataset in which you have a goal and you have a sequence of frames associated with the different sub-goals that should be carried to perform the final task. And in terms of model, usually it's look like this. You have a goal, you decompose into a plan, and at the end you have to do the alignment between the plan and the logic actions. Regarding the abilities of large language model, one question is why it is useful. So I try to summarize different perspectives. So the pre-training model have general knowledge and planning abilities, so it allows to decompose complex action into sub-actions. So this is the most obvious possibilities of using large language model. But also, since you have this general knowledge and the semantics behind concept, you have a representation of linguistic instructions, the visual scenes, if you use visual language model or also foundation models, and you can also label data for evaluation. I will also mention that in different examples. Regarding the prompting ability, it allows to provide the context. So what is the context? It might be the task, the current state. You can describe the scene. You can provide some information about the current execution of the action, and also provide different examples. So in context learning, allowing to generate action, explain also errors or the current situations, provide external feedback, and learning with less annotated data due to the in-context learning. Also, I mentioned this in the last item, in context learning or the fine-tuning ability with small data allow to have quick adaptation to new tasks. So in the next slide, I try to do kind of summary of the literature review. It will maybe mention some works you have presented in the presentation yesterday and also today. And I mainly focus on the model, not on the evaluation part. Because I was focused on the use of the LLM on those different work. So the topology of model, so I here present the two extremes from my point of view. The first one is having contextualized sequence-to-sequence model in which you encode and decode the text for instruction generation. So you provide the goal in text and images or related to the environment, and you expect the model to generate the different instructions. So here are different example of model. So this one is called SL3, in which you provide the image, you embed the image, and also you have an embedding of the text. And then you can condition the language models according to those two embeddings to provide the different actions. Another one is called SeiCan. Maybe it has been mentioned yesterday also. The objective is to use large language model to provide a plan, just here. And also given this plan or given the initial goal, we have a value function related to the scene, and what we do is to compare the probability provided to the large language model with the value function provided by perceptron model, and then combine those two scores to provide the next token given a sentence, so given the beginning of the instruction. And on the opposite side of the chronology or the topology of model, you have what we call foundation model or visual language model and multimodal language model, which are pre-trained model with semantic, visual, perception information, and it might be assimilated to general knowledge of robotics. So here is an example. We have the model CLASP. CLASP is a model in which they learn a multimodal space, including text, behaviors, and actions. In behavior are represented by images, but the objective here is to learn this representation space. And to learn this representation space, you have different losses. The first one is a loss aligning the vector representation of those items, so images and the text when they are aligned in the training data set. There is also a loss captioning behavior, so generating a description according to a frame in the sequence of action, and also a behavior generation in which you provide a different action or a single action given a frame associated to a behavior. As a limitation of this model is trained on the language table dataset, which is a quite simple dataset, but in terms of formalization, it might be a first step toward foundation models, but it should be extended toward a more complex task and more diverse task to have general knowledge regarding the robotic task, in my opinion. Another one is called Voltron. The objective is for Voltron is to train a transformer encoder, a multimodal transformer, in which you provide the goal in a natural language, and also some frames which are sparse here. And the objective is to train this model by reconstruction loss, one to reconstruct the images, the full images, so to do some inpainting with the images, and also to have the reconstruction loss regarding the textual instruction. And the assumption is you learn this multimodal interaction and maybe also those perception cues. You can learn these perception cues within the transformer encoder, and then you can use the transformer encoder to do some different tasks. The first one is language conditioning, in which you solve visual tasks such as segmentation, grasping, or imitation. And the second task is language generation, in which you can generate a language instruction or scoring for intents regarding the goals and so on. A third work towards a foundation model is the PALM-E model. Also, it used prompting as the previous work, in which you can provide text, which is the goal you would like to achieve, for instance. You have also text related to entity properties, the functionality, some properties related to the entity. You have also a representation of the states, which might consist on the pose, the size, the colors of objects, which are represented using an MLP. And also you can use vision transformer for 2D and 3D features related to the object and the scene. And you provide all this information as input, as a prompt of the language model, and at the end you solve the targeted task, and you learn those multimodal large language model here. So just a summary, this is the two extremity of the topology, but in the middle we have a lot of variation of model, and I will present you some of them and how the large language model are used mainly. So here this is a combination of both words in which you have a foundation model here, which is called here grounded, that take images and text and also provide different capability. And the objective is to provide probability of different tokens according to this multimodal context. And this is the probability are also combined with the probability provided by an LLM as the previous work, but here you have a large language model rather than just a vision model. You have here another work in which large language model and vision language model are used, but in a sequential way. First, we use the large language model to generate sub-action or sub-goals for the plan. And then the visual language model align those sub-actions with a different frame to provide a multimodal context. And then at the end, you have a policy network to choose the action you have to do according to this multimodal concept. So the visual language model is a clip model in which the representation between the text and the images are aligned using a dot product. Also, another topology of work using a large language model or visual language model is to use those models to describe the current state at a timestamp of the sequence of actions. So here we have different agents communicating with each other. So we have the robot that predicts the action he has to do according to a goal provided by a human. And this robot can interact with two agents. The first one is a scene descriptor, which the objective is to identify the objects within the scene. And you can interact with the scene descriptor in a passive interaction, so just an object detection task as a vision in the vision community, or also an active interaction with visual question answering, or for which you ask questions to the scene descriptor, and then it provides information regarding the objects. So the first component is a scene descriptor, and also you have the success descriptor, which is a classifier which produces whether the task, also the action here, will be successful or not. And this is actually a classifier which is trained on real examples and then used as inference according to the current situation. So here, large language models are both used to describe the scene and also to interact between agents. And this is quite similar here, but what is different is that the LLM do not provide instruction in natural language, but directly has logic commands. So here, and then it interacts with a robot which is embodied within an environment and can provide also a description of the environment and also what it can do or not. And the plan is refined according to those interactions. And for me, it was really interesting, this paper, because the early work before this have shown that expressing sub-action in natural language was more effective than provided command action, and it was more able to have accurate plan. They provide also a more accurate plan than those instructions. But what is done here by the LLM, and they don't claim a lot in the paper, is that they use in-context learning. And by using in-context learning, in which you provide the example of how those commands, which might be sometimes not understandable by the LLM, but you provide some example, and then the model is able to capture how to reuse those command action within a new task. And I think it was one of the first work I have seen providing very effective results for doing that. And my perspective changed actually when I read this paper, because I say, okay, maybe we can just use LLM for doing interaction and provide some grounding of the scenes and the objects and so on, and directly go to the logic command rather to use this intermediate space to state to generate natural language instruction, and then have the challenge to map the natural language instruction with a logic command, which is also challenging in terms of research. So here you have an example of how it works. So the model provides us different interaction, and you have this in-context learning example, and then you can refine the prompt according to what is provided by the robot and the object detector, and provide some information to refine the plan, and then provide a new plan according to this. In the same mind, just to put the focus on which kind of plan can be generated, here you have symbols of the Minecraft data set, and therefore you can see that you can generate symbol rather than natural language instruction. And here the process is quite similar. The large language model provides this plan of symbols. Then you have a controller that executes this plan within the environment, and a descriptor that identifies what has been successful within the plan and what has been unsuccessful within the plan. And then according to this description, the language model can also provide a new plan and then revise until the whole plan is successful for the task. Another category of work using large language model target to call external tool. In the NLP community, we have a paper called Toolformer, maybe you might know, and the objective of Toolformer is to generate tokens using probability, but also to learn how to call external API to improve the factualness of the generation. For instance, you can learn to call calculators, you can learn to call visual question models, you can learn to call summary model, translation models, and so on, and therefore get the answer of this external API to reintroduce this output within the generation. And what is done here is to leverage maybe this philosophy of calling external tool and learn how to generate a prompt to have different things, but also to call those external tools. And those external tools here are external agents or model that can, for instance, find the target or find information about the landmark around the target. So the model here mainly consists in generating the prompt here to fed to the large language model, and then this large language model has to generate the sequence of instruction and so on. But what is interesting in the prompt, they learn to generate this prompt in three parts. The first one is the observation, so what the user is looking for. A reasoning part is what we need to perform this task, and then the plan using the call to different external API. So here in the plan, for instance, you have called the target finder with the wooden shell, and then call the landmark finder with the table. So you have the property to feed to those external API, and then different steps. And according to the output of those targets, the prompt is rewritten here by taking into account those information to have the factual information inside the plan. No, this is not the last. I have the last one. How many times? I'm fine. Okay. One other interesting property here is the ability to fine-tune the model and see how it evolves during the environment. So this is a paper proposing a model calling GLAM. The objective, so it is mainly focused on text. We don't have here vision input at the model, but this is interesting regarding the fact that they fine-tune the model. And the objective here is to describe the environment with sentences. So you have different natural language sentences here. And then you can build a prompt to provide to the LLM, and then the LLM can identify what are the next action to perform according to the probabilities. And this model is fine-tuned according to an environment in which you have a reward, and then you apply the PPO algorithm to fine-tune the model. And what is interesting is that obviously it improves the effectiveness of the model, and it will be also interesting to identify what has evolved through the time according to the fine-tuning, to see what are the affordances we introduce within the model, and what is captured according to the environment, what is missing in terms of semantic within the large language model regarding the execution of tasks in a real scenario or environment. And here, this is quite similar work for which the objective is to fine-tune a language model, but it is done according to the generation of new data given an environment. So you have here an environment with a robot that has to perform different tasks. And according to those different tasks, you have two models, a goal-oriented planning and a random exploration. So you have a model targeted on the realization of the task, and here on having more diverse trajectory for solving the task. And according to those models, you can generate some data. I will show you in the next slide how to generate those data. But you have some additional supervision data that can be used to fine-tune the model. And what they have shown is that when you ask some different tasks regarding the counting of objects within an environment, tracking some objects also within a scene, or generating a plan, when they compare to ChatGPT, the output of the fine-tuned LLM according to this environment is more accurate. So the whole question is, how do they generate those data? What they have done is, regarding the goal-oriented planning, is to generate experiences within an environment, and then they have expressed different predicates according to the action performed within the environment. You have different predicates such as walk to bathroom, walk to bedroom, and so on. And they have associated transition probability according to the real experience simulated within the environment. And according to this tree, you can design some new tasks such as plan generation, so given an objective, generate the plan, or activity recognition, so given a plan, identify the initial goal. And this is obviously completed according to the analysis of the tree through Monte Carlo tree search. And then using this, you can generate new data to feed to the LLM. And this is quite similar for the random exploration model. So you generate experiences within the environment. You record the moving path and the final object locations. And at the end, you design different tasks. So here, counting objects within a context and tracking the object path. And then also you can simulate and generate different data. And the last model, I think, also is also focusing on the fact that we can use the large language model to generate new data. When you have a simulation, you do a lot of trajectories, and in those trajectories, a lot of them are often unsuccessful, and therefore you might have a sparse reward. And therefore you can use those unsuccessful trajectory to transform them into successful one. And this is what we call insight experience replay. So we convert failed trajectory into successful ones, and therefore we need to identify what was a successful goal for those unsuccessful trajectory. And for doing that, they used large language model to annotate the strategy and to annotate particularly what is the last object picked up within the scene, to identify those properties and then generate new goals according to those strategy which has failed initially. And for doing that, they use prompting with a large language model, and they ask the model to identify what is this object, what is the color of this object, and so on, and to design new goals according to those unsuccessful trajectories. And then you can fine-tune the model according to those additional data. Okay, so just as a conclusion, I have tried to summarize different strategies to use or design large language model or foundation model for robotics, but they are a lot of open research questions. One of them, maybe I have said few words earlier, but it is about the planning, what we should plan. Should we plan natural language instruction or directly the logical actions? So some work have demonstrated that maybe this intermediated step with large natural language expression might be not useful and maybe might also complex the process, but we have also to go deeper into this. The question is also how we can use the grounded of the environment. Should we ground the objects, the entities, the scene, or also use the execution to have better affordance of what is the environment, of what the model should be done? So obviously, I think it should be better to have execution, but we know that doing the whole pipeline might be also complex, and sometimes we go just at the object and entity and scene levels with no real execution. So can we, a related question is, can we capture affordance without controller? So maybe Cordelia has also mentioned the necessity to use different point of view from an image, and maybe it might be sufficient, but is it sufficient? This is also maybe a question. Related to our project is, do LLMs or foundation models are sufficient generalization property to design autonomous robots? So I think it should be interesting, as I mentioned, to analyze the large language model we fine-tune to identify which knowledge are preserved and which knowledge evolve, to identify what can be generalized and what need to be specified according to the task. And also, is the prompting sufficient to raise the knowledge? Context learning have shown very good properties to inject new example and to learn new inference between different tasks. But is it sufficient when we have a lifelong learning setting with a lot of successive tasks? If we provide too much example within the prompt, does it fail in terms of effectiveness? And I think those are open questions we need to solve in the next year. Thank you for your attention.
Thanks a lot, Laure, for this survey. And so we can take now a few questions, if any, in the room or in the audience, but I think the chat is a bit deactivated. So any question in the room? I can start with one.
Yes.
So maybe can you share a little bit more on what you are currently doing at EASY or in this EU project in terms of preferred topics?
Yeah. So as I mentioned, there are different working groups. So some of them are working on visual model reinforcement learning and also on the bridge between models with robots, and so doing some real settings in real experiments. But for the NLP part, we have started to work a few months ago on the generalization properties of large language model. What we have done is to consider the two extremes of the topology I've mentioned earlier, so contextual sequence-to-sequence model and foundation model, and see how they behave in terms of generalizations. So for instance, you have a task, the task of generating instruction. And in the training set, you have different instructions such as grab the knife. And what we have analyzed is if you provide different words that are not seen within the training set instead of the knife, so such as a stencil, such as the vase, and so on. And also, we have done some mapping with the environment, and we have identified different settings in which you have a vase or not, you have the knife or not, you have a lettuce, and we have identified different mapping between the instruction and the object present in the scene and see how this model behave. Actually, we have preliminary results, so they have to be strengthened. But what we have seen, and maybe this might be obvious, is that contextual sequence-to-sequence model rather focus on the image to take a decision of what to do, what are the objects present in the image, and then they generate the instruction according to this image. And the foundation model rather focus on the language. And so we have those two differences, but we have to analyze in more example. And we have a thesis starting next month. And I think we will first begin by analyzing what we learn in a large language model, what are the semantic we can keep when we fine-tune the model according to the task, what I mentioned earlier, and see how we can provide lifelong learning strategies when we adapt to new tasks. Let's see.
Thank you for the answer. Okay, so now there are questions in the audience. I start with Stéphane and go back to you, Gérard, after this.
So thank you, Laure. Can you say a few things about the efficiency of the LLM for robotics? Is it a big deal or not? Do you see some application where it is important or not at all?
Oh, I don't know if I have the answer, actually. I think it depends on how you use it and which information you provide as input. But since we need to, I think we will need to capture more and more information. So therefore, designing kind of foundation model which will be more effective. But actually, maybe in 2 years I can say more about this. Sorry.
Okay, thank you.
A scientific question for a change. Are you aware of any work trying to see if this large language model have a theory of mind? So is that possible, in fact, to questions and coupled with clips? So the scene understanding and decoding the intention of the agents.
Yeah. This is a discussion we had in the lab because I know that some people are interested in this, and we have to discuss more and more about this. But yeah, actually in NLP, I work on information retrieval, and we have a task which is called clarifying question. Which actually, when I discuss with the robotician, can be related to this theory of mind information. And for generating clarifying questions, the objective is to understand the intent behind the user and then to clarify and to at the end. And we discuss how we can take those work to bring them also in large language model, and those roboticians dealing with theory of mind discuss also, but yeah. Let's see.
Any more questions in the audience? I have a last one, maybe.
Yes.
Let's say that we are mostly interested in using LLM for planning.
Yeah.
My question is it enough to use in-context learning for doing planning with pre-trained LLM, or should we train them specifically for this or fine-tune them specifically for this?
I think this is difficult because in LLM you have a lot of general knowledge, and you might assume that when you have simple tasks using the parameter within the model, or maybe some in-context learning might be sufficient. But if you are very complex task with very specific data, for instance, with a surgery application and so on, maybe you have to fine-tune. But maybe it is sufficient to provide some information about the tools you use in a surgery, in the in-context learning, to bring the knowledge to the task. But yeah, it might be also investigated. I have not seen a lot of work analyzing the impact of in-context learning in robotics. So maybe we can discuss.
Okay, thanks a lot for the answer. And let's thank the speaker again. Thanks a lot.
Thank you.